So we're going to look at the introduction to Chapter 5, and Chapter 5 is all about the system of linear equations. So we're going to go over some background information and then preview what the unit's about. So before we talk about systems of linear equations, let's talk about where we've been. So up until now, we've been solving just equations. And all the equations that we've been solving at a time, I've just been giving you one equation at a time, and those equations have one variable in them. So just some examples of those, like on the left side here, this is one equation. And there's only one variable, which is x. So if you're going to tell me the answer, you would tell me that x was equal to 2. This equation over here, again, there's just one of them. It has one variable, and that variable is y. So then, like when you were solving it, you would tell me that y would be equal to 8. This last equation, again, we can see this is just one equation, and in that equation, there is one variable called w. So when you would solve this, you would tell me w would equal something. I believe here it's 1. So we've been working with just one equation at a time. And with that, that's a really important piece of information. If I give you one equation, you can solve for one variable. So here we have a counter example. So like down here, this is one equation, but it has two variables. And with this, I cannot solve for this. So think about how we would. If I tried to get a variable, I'd have to get something alone. So here, y is already alone. But I need to get rid of x to find y. If I try to rewrite it as something like y plus 6 over 3 and get x alone, that doesn't help me because I still don't know what x is. So again, if I have two variables in one equation, I'll never be able to tell you the answer as a single number. But if I have one equation and just one variable, we can always answer those. So as we said on the last screen, if I have one equation with one variable, I can get one answer. And we know that the solution, or no, the answer to our equations is just the number that makes the original equation true. So for example, on this one here, I know the answer is x equals 2, because if I plug it in, I do get a true statement that 0 is equal to 6 minus 6. So that one works. On the next one, if I think the answer is 8, I would just plug it back in, and it would make the original equation true. Half of 8 is 4, and 4 is equal to 4. On this last one, if I wanted to see if this was the right answer, it would be plugged back into the original equation, and it should make that original equation true. And in this case, it does. 3 plus 2 is the same thing as 1 plus 4, or in other words, 5 is equal to 5. So we know the solution makes the original equation true. We've also seen that some of these equations might not have solutions, or maybe they have an infinite number of solutions. So just as a quick example, over here, when would the equation x plus 2 equal x minus 3? Well, that's never going to happen. If I take a number, let's just look at that. If I took a number x, if I add 2 to that number x, it's never going to be the same thing as if I start with that number and subtract 3. So we've seen examples before where there are no solutions. And when we see a solution that says, or when we see an answer of no solutions, what we're saying is no matter what number we would try to plug in for the variable, it's never going to work. So I just randomly picked 3 or something like that. When I plug in 3, I can see I get something that's not true. So something like x equals 3 is not a solution. No matter what I would choose, I wouldn't get an answer here. But over here, we've seen some situations where maybe there's an equation that's always true, no matter what we plug in. So something like this. If you did the distribution and stuff, you'd see that this would boil down to 6 equals 6. And this is going to work for any single number. So if I pick a number in here, I just try to random number like 12. If I plug it in, I get a true statement. So we've seen some special solutions as well. No matter how we're coming, or no matter how many solutions there are, or if there's infinite or none, we have different ways of getting those solutions. So one of the most common ways is the algebraic way. And that's just most of the ways that we start. We just use, we undo operations, like add 1 to both sides. So 3/4 x is equal to 9. And I could undo dividing by 4 by multiplying both sides by 4. When I do that, those would cancel, so I get 3x equals 36. And if I divide by 3, I get something like x is equal to 12. So we have some algebraic ways of doing it. We also could use a graph. Let's say I was asking, when is this line 3x minus 6? So I've graphed the line 3x minus 6. And if I have a graph of something, I could ask, when is it equal to 0? Well, that's equal to 0 right here. So this would, when x is equal to 2, Well, the y value is 0. So I could use a graph to do it. Same thing, just as another example. When would this line be equal to -3? Well, here I can see the y value is -3 when the x value is 1. So we have different ways of finding the answers. We can do it algebraically. We can use graphs. Now, the new stuff we're working on is a system of linear equations. So rather than just one equation, when I say a system, it's a set of equations, meaning there's going to be two or more. So a set of two or more equations, and as a qualifier, they have to be using the same variables. So just as some like basic examples, like something like this, like x plus y equals 12, and 3x minus 6y is equal to 42. That is a system of equations. So there's two equations with two variables, x and y, in both of them. As another quick example, I could do something like z equals 4, x plus y plus z is equal to 24, and then maybe something weird like 3y minus 4z is equal to 2x. So this one has three equations, and it has three variables. And those variables are x, y, and z. Something like this, like y plus 2x equals 3 and z equals 10. This is not a system because they are not in the same variables. Now for us, in our class, we're just going to focus on 2 in Algebra 1. In other classes, you'll see 3 or maybe 4, but for us, we're just going to focus on 2. So the next big idea in our notes is that the number of equations that we have will always match the number of variables that we can solve for. So we saw that before, right? When we were looking at just regular equations, we had like an example like 0 equals 3x minus 6. We got x is equal to 2. So if we have one equation, we get one answer. That's where we've been before. So the new stuff that we're going to talk about, well, if a system of equations has more than one equation, we could have two of them. So if I have two equations, we can solve for two variables. If I have three equations, then we'd be able to solve for three variables. And it does work backwards too. If you're working on a problem that you have two variables you would need to solve for, you would have to be able to write two equations to get their answer. If you're going through a problem and you realize you had three things that were unknown, to solve for that, you would need three different equations. So the number of equations will match the number of variables, which will match the number of answers we can find. We know what the solution to one equation is. If we have an answer, we plug it back in and it makes it true. But when we have a system of equations, right, the solution to a system are the variables that satisfy all the original inequalities, and for us it's just going to be 2. So for example, let's say I have this system of equations here. So there's two variables and there's two equations, so we should be able to find an answer for x and for y, and they want us to check to see if this point here is 3, 4 a solution or is 2, 5 a solution. So what we're saying is if it is a solution, it'll make both of them true. So let's go ahead and first try the first point. Let's try the point 3, 4. So if it is a solution, we'd have to plug it into both. So it'd be, instead of x plus y equaling 7, we'd plug in x is 3 and y is 4. So we do get that 7 equals to 7, so it makes the first true, but it needs to make both of them true. So let's go ahead and try the second one. If I plug that in, 2 times 3 minus 3 times 4, well, that's going to be 6 minus 12, which is negative 6. And negative 6 is not equal to 11. So this point, 3, 4, is not a solution to the system because it doesn't satisfy both originals. Now if we go try the other point, if we try the point 2, 5, what we see, it will make the first one true. If I took the x value of 2 and added it to the y value of 5, I do get 7. So 7, that's a 5. 7 is equal to 7, so it makes the first one true. But we have to check the second one. So 2 times 2 minus 3 times 5. Does that equal to negative 11? So we get 4 minus 15. So we get negative 11 is negative 11. So this one is a solution because it satisfies both. Now, just like with equations, a system of equations can have answers, like we just saw before, x was 2 and y was 5, but they can also have special solutions. Now, these are just representations. We're not asking you to find them yet, but I would say the three types of special situations we could have a situation where there's no solutions. We saw that before. In our linear example, we saw something like x plus 2 will never equal x minus 3. So we've seen that with equations. The same thing could happen with system of equations. We can also see points where they have no solutions. So example, when we looked at before, infinite solutions. We saw something like 3x plus 2 and the equation 3x plus 6 had any real number. So in systems of equations, we can also have those special situations. Aside from the fact that we just have a point, and we went through that one just before, like the other type of answer we could get would just be, just like one solution like we just saw before. Like maybe we have the equation like 0 equals 3x minus 6, so we saw x equals 2. And the example before, we saw that the answer like 2, 5 was an answer. So whether we're doing systems of equations or whether we're doing regular equations, we have the special solutions. We could have no solutions, or we could have all solutions as well. Just like when we solved equations, when we solve systems of equations, there's going to be many different ways that we're going to be able to do it. So for you today, I'm just listing them. You don't need to know how to do them. Every day of the unit will be a different day on studying one of these methods. But just so you know, just like with linear equations, there's the same methods that we have for systems of equations. Rather than just one equation, we can apply them to more than one. So just like when we did it by hand with, or when we solved just one equation, we can do things algebraically. Now there's two methods that you need to at least be aware of. And again, the steps right now are not important, but the names. So you need to write down the names. So we could solve the system by elimination or substitution. So those are two of the algebraic methods. So there's two ways to do it algebraically. And then just like we did with the with one equation, we can solve two equations graphically. So we're just trying to draw connections that we can do these types of problems the same way that we can do the other types of problems. And there is one way for us to do it on a graph. And we will be learning all of these ways as we progress through the unit. So linear equations, just solving an equation, is what we've already done. So we can kind of consider that we already know. But this new stuff, systems of linear equations, is something new, but they're very similar things to what we already know. So if we can kind of start to keep them organized, we'll be able to better perform in this unit. So we're going to compare and contrast what we already know and the new thing we're going to get into. So the number of variables matches the number of equations. So like first of all, what I want to write down, this is true. So we say yes. When we just have one equation, we're saying there's one equation, which means there's one variable. In our new unit, this is still going to be true. Yes, the number of variables match the number of equations, but we will have two equations and two variables. Now, for just one equation, right, the linear equation, the solution will satisfy the original. So we say yes, there's one answer, so one value, and it makes one original true. The same thing will be true for our system of linear equations. Yes, but we have two values that make both equations true. There will be special solutions. Yes. And the special solutions we'll see are something like no solutions, which I'm abbreviating, or infinitely many solutions, which I'm also abbreviating. That's the same thing we're going to see with system of equations. There could be no solution to the system, or there could be infinitely many solutions to the system. When we're solving just one equation, we can totally do it by hand. Like if we saw at the beginning, we would just undo the operations. And we call that algebraically. With systems of equations, we can solve them algebraically. We have two methods, though. So when we're solving one equation, there's pretty much only one way to do it. We got to undo the operations. When we have a system, we can do it by hand, but there's two different methods that can be used. And again, you don't need to know those methods yet. We'll teach you along the way. But understanding that for both of these types of scenarios, we can do it by hand. And both of these things that we know, like the just solving a single equation, we could use a graph to solve that. And when we move on to a system of equations, we could also use a graph to solve that. So studying what you already know, what we know with one equation, can help us apply to more than one equation.